So, let's talk about the magic behind the apps we use every single day. We're going to dig into some of the brilliant, kind of hidden ideas from Martin Kleppmann's incredible book, Designing Data-Intensive Applications, to really get a handle on the systems that basically run our digital lives.
You know, when you open up your favorite app, it just feels so smooth, right? So simple. But what's really going on just under the surface is this wild, powerful, and unbelievably complex world of data and engineering. It's a beast.
Think about it. We do this stuff all day long without a second thought. You tap a button, a car shows up. You search for a photo from years ago, and bam, there it is. It honestly feels like magic, but it's not. It's engineering. So what does it really take to make it all just work?
All right, so let's do it. Let's peel back that curtain on this illusion of simplicity and take a good look at what's actually happening inside the services we rely on every day.
And that really is the core paradox here, right? For us, the users, everything is slicker and easier than ever. But for the engineers behind the scenes, the challenges have just exploded. So why is that? What makes building these systems such a ridiculously hard job?
Well, to get to the bottom of that, we have to meet the bad guys in this story. There are basically three fundamental forces that are constantly trying to break, slow down, and just generally mess up every single data system out there.
Okay, so first up, things break. I mean, everything breaks. Hard drives die, networks get congested, there are bugs in the code, and yep, we humans make mistakes. Second, you have just massive, unpredictable numbers of people using the system all at once. And third, over time, these systems just grow and grow until they become these tangled, complex webs that are incredibly hard to understand.
And here's something that might surprise you. When we talk about things breaking, we always want to blame the hardware, right? But one study found that hardware failures only cause about 10 to 25% of outages. The leading cause? Turns out, it's us. Simple human error, like a misconfiguration.
Okay, so those are the problems. What about the solutions? Well, for every one of those big challenges, engineers have a goal, a guiding principle that helps them build systems that can actually fight back. And this is the perfect way to think about it. To fight against things constantly breaking, you aim for reliability. To handle that massive, unpredictable load, you build for scalability. And to tame that growing complexity, you have to design for maintainability. Reliability, scalability, maintainability, these are the big three. You got to remember them.
So, what's reliability? It's actually a pretty simple idea, but it's incredibly powerful. It just means, can your system keep doing what it's supposed to do, and do it right, even when some parts of it are failing? It's all about expecting failure and designing for it from the start.
Next is scalability. This is all about what happens when you succeed. What happens when your app goes viral overnight? Can your system handle it? You've basically got two choices. You can scale up, just get one gigantic, super powerful computer, or you can scale out, which means spreading the work across a whole army of smaller machines.
And this last one, maintainability, this one's for the humans. It's for the poor engineers who have to live with this system every day. It means building things in a way that's understandable, so that someone new can come in and fix a bug without having to understand the entire terrifyingly complex system from top to bottom. Good abstractions are everything here. Now you might be thinking, okay, great, just max out all three of those, right? Make it super reliable, super scalable, and super maintainable. Well, not so fast. In the real world, it's never that easy. Engineering is really all about trade-offs, this constant balancing act, where the correct answer is, well, it's complicated.
This sounds like some kind of brain teaser, doesn't it? But it's not a trick question. It's a very real, very weird thing that happens all the time in large-scale systems, especially when your data is spread out all over the world.
Okay, take a look at this. It's a fantastic example from the book. You've got Mr. Poons asking a question. Then you've got Mrs. Cake giving an answer. Seems normal. But there's a third person, an observer, listening in from somewhere else. Because of the way data travels across the network, that observer hears Mrs. Cake's answer before they hear the question. From their point of view, she's psychic. And this isn't a bug, it's a consequence of a design choice.
So what you just saw, that weird psychic effect, that's called replication lag. It's that tiny, tiny delay between something being written to one computer and showing up on all the other computers that have a copy. And in that little window of time, the system is technically inconsistent. So engineers have to consciously decide how much weirdness are we okay with in order to make things fast.
So the big takeaway here is that there's no magic bullet. There's no single right way to build these things. It's all about understanding these deep trade-offs between speed and correctness and cost, and then making deliberate, informed choices about what matters most for your specific application. And that brings us to our final point, and honestly, it might be the most important one of all, because the choices engineers make aren't just technical, they have real consequences for real people, and that adds a whole other layer of responsibility that goes way beyond just code and machines.
Martin Kleppmann puts it perfectly in the book. He says that the people building these systems have a duty, a real responsibility, to think long and hard about the impact of their work. It's not enough for a system to just work well. We also have to ask what it's being used for. And this forces us to grapple with some really serious stuff. Like, if you feed a system biased data, the algorithm doesn't just learn that bias, it can actually make it worse. Or how making it super easy to collect massive amounts of data can slowly make total surveillance feel normal. And we have to remember that data isn't just numbers in a spreadsheet. It represents real people.
The bottom line is this. The systems we build aren't just shuffling bits and bytes around. They are actively shaping our lives, our opportunities, and even our entire society. These technical decisions have a profound human impact.
And so that leaves us with a huge question, not just for the people building these things, but for all of us. As these incredibly powerful systems continue to weave themselves into the fabric of our world, what are we actually asking them to do? What kind of world are we asking them to build for us?